Hello, this is Aashna Patel, and this is my Physics 2211 Section K Lab 5 Motion of the Falling Slinky lab report. So before beginning this lab, it was important to consider a few important formulas, the first being Newton's second law, which states that F net equals dp over dt. In addition to this, a slinky is basically a giant coil, so it was most important to understand the spring force and the spring constant in general. So as stated here, F spring is equal to negative K times L minus L naught times L hat. And important to also understand the force of gravity as listed here. Additionally, it was also important to understand the energy principle of the change in energy, change in potential gravity, change in spring, and change in potential spring energy. To continue, this was the experiment as stated here. I first began by finding a video of an object in motion at constant speed without changing in direction, basically a slinky falling. I then analyzed the recording using the tracker app to find the object's observed position and corresponding time, and then created an experimental model to reflect the movement of the object. After this, I created a glow script code based on the Lab 2 original code and identified areas to match the observed data provided in the tracker app. Using the code, I then found a theoretical model using gravity. Finally, I compared the results of the observed and predicted data. So here's the video in tracker. As you can see, the slinky falls at a constant speed, and the bottom stays in position until the top meets up with it, which I will explain later in this video. So from the tracker video, here is the observed model found from the points. It took into account the force of gravity acting on the object and shows that the object fell at a constant speed while decreasing in position. After this, I used those points to create a glow script code. So here I inputted the mass of the slinky, the delta t, and the position of the slinky in motion. I then used the time to create a calculation loop and inputted the formulas as seen here. And once again, here are the formulas that I put in. And finally, this was the theoretical model found based on the data observed. This also took into the account the force of gravity acting on the object. As seen here, it was a pretty consistent line with a consistent velocity. So in comparison, Series 1, which is the observed data from tracker, and Series 2, theoretical data from the glow script, there is a large discrepancy in the models. The video was taken for the observed data in tracker. The video was taken outside and had forces including wind, which may have not been accounted for, which played a large role on the slinky. So, in conclusion, why does the bottom of the slinky remain still when falling? Essentially, the bottom coil of the slinky is at rest because the tension on the slinky pulling it upward and the force of gravity pulling it downwards are equal and opposite, relating back to Newton's second law. So, when you let it go, the spring force will try to accelerate the two ends of the slinky towards each other, the top end going down and the bottom end going up. However, the bottom of the slinky won't move because it has no net force acting on it. In this case, gravity and spring force cancel out. Overall, I thought this was a very interesting lab, and learned this helps me have a